scalability of Bitcoin and this whole discussion of how to keep Bitcoin decentralized, but also make it available to everybody. So scaling it up to huge numbers of people and huge numbers of transactions. And in this discussion, the Lightning Network is often presented as the technology that's going to save the day for Bitcoin. And the technology behind the Lightning Network is called microtransaction channels. And in this talk, I'm going to explain this technology to you. My name is Corne Plooy. I am a developer of AmicoPay. AmicoPay is a project that's already a bit older than the Lightning Network, but it aims to accomplish a very similar system. And since AmicoPay has now adopted most of the concept choices of the Lightning Network, it's more or less the same thing. So let's look into how these things are going to work. In this talk, I'm going to I've split it up into a couple of parts, and in each part I'm going to explain a slightly more complicated and advanced design of a microtransaction channel, and maybe we'll have some time for questions in between to keep everybody focused. So before we start with that, first small look at Bitcoin transactions. Basically, a Bitcoin transaction has inputs and outputs, and the inputs specify where the money comes from, and the outputs specify where the money goes to. Or actually, the output specifies the conditions that have to be met before somebody can spend that output. So in an output, effectively a script is specified, and that script is executed whenever somebody tries to spend that output. And that is done to check whether the spending transaction is valid or not. So you can use all sorts of conditions on this spending. You can say, well, it needs one signature from one person, or two signatures from different people, or it can require, it can have a timing requirement, or all sorts of different kinds of conditions can be expressed in this scripting language. And well, the most regular type is, of course, that just one digital signature is needed. Now, let's give an example use case of Bitcoin. Suppose that there is a public Wi-Fi hotspot, and for this public Wi-Fi hotspot, the owner would like to charge a very small amount of money for using that Wi-Fi hotspot. So one way to set something like that up is if the customer, let's say Alice on the left, first uses the Wi-Fi hotspot for a couple of minutes, and then afterwards she pays for that with a Bitcoin transaction. That is a bit problematic for the owner of the Wi-Fi hotspot, because now this owner has to trust that Alice will pay for the service. And of course, Wi-Fi doesn't end at your walls, so somebody outside could just use the service and then walk away. So you cannot really trust the other party. So this way of work is unreliable. Another way to do business could be if is a prepaid system where Alice first pays a certain amount, and that gives her the ability to use the hotspot for a while. And then when she is finished, she says, well, hey, I'm finished. And then she gets the remaining part refunded. But in this setup, it's nice for Bob, but Alice has to trust Bob in this case. First of all, Alice has to trust that she will really get service. And secondly, she has to trust that she will get refunded in the end. So if neither party can trust the other, this is not a good way to do business either. So one thing you could do is split up the service into very small parts. Let's say 1 minute of internet access, one payment, and another minute, one payment, etc. And that reduces the risk for any party to a very small amount, so that could make it acceptable. There are some problems with this setup. Let's say you use 80 minutes of internet access and 1 payment per minute. It means you do 80 Bitcoin transactions. And for each of those Bitcoin transactions, you have to pay a transaction fee. So especially when the block size is quite limited, that's going to add up all these transaction fees. And another problem is you have to wait for confirmations to be sure that these transactions are definitive. So on average, you have to wait 10 minutes, but if you're unlucky, it can take maybe an hour or something like that for the next block to arrive. So that's not convenient when you're talking in the order of minutes here. So using regular Bitcoin transactions is not the best approach in this example. And somewhere in, actually there's already quite an old idea in the, that was described, I think, first by Mike Hearn. I'm not sure if he's the first to describe it, but it was already there in 2011 when I joined with Bitcoin. And the idea that is called microtransaction channels. And how does it work? Well, let's start with the initial situation. The initial situation is Alice has some Bitcoins. And what does that mean? It means that there is a transaction somewhere on the blockchain that has an output of a certain amount of Bitcoins that can be spent by Alice. Alice has the private keys that give her access to that output of that transaction. And with the green lock signal, lock symbol here, I mean it is placed on the blockchain. I mean, basically, when something is placed on the blockchain and it gets a couple of confirmations, it becomes definitive and unchangeable. So that's why I use a sort of a lock symbol in this presentation for that. So Alice has 1 million Bitcoin. Now, in order to create this microtransaction channel, Alice creates 2 new transactions. First transaction here spends the outputs from herself and sends those the Bitcoins to an output that requires 2 signatures, one from herself and one from Bob. So Alice adds her signature to this, and her signature is necessary because it is required by this transaction. So this is a valid transaction. Alice could publish this on the blockchain, on the Bitcoin network, and that would get it included in the blockchain. But for now, she doesn't do that yet. So for now, it's just a piece of data on Alice's computer. The other transaction that Alice creates is this transaction. And that transaction sends the Bitcoin back to Alice. So it has an output that only requires a signature from Alice. Now, this transaction is not yet valid because it requires 2 signatures, one from Alice and one from Bob. Alice could add her own signature here, but that's not enough. She needs the signature from Bob. So what Alice does is she sends this transaction to Bob. Bob looks at it and says, well, hey, this transaction is not spending any of my Bitcoins, so I don't really care. Whatever, you have my signature for it. So Bob sends his signature to Alice. And now Alice is able to get her Bitcoin back, her Bitcoin back with this transaction because she can add her own signature to this. And then this becomes a valid transaction. So now that Alice is certain that even without future cooperation of Bob, she is able to get her funds back. Now, at this point, it is safe for Alice to put this transaction on the blockchain. And at this point of time, the transaction channel is open. So this was all initialization steps. And from this point on, we can start doing microtransactions. Now, how does Alice make a microtransaction to Bob? Simple, she makes a new version of this transaction. So it spends the same output, but instead of sending all the Bitcoins back to herself, it reduces the amount that is sent to herself, and she sends a little bit of those funds to Bob. So this transaction has two outputs. One with 0.99 millibitcoin to Alice, and one with 0.01 millibitcoin to Bob. Alice signs this transaction and sends it to Bob. Now, when Bob sees this transaction, he can see, well, it has a signature from Alice. It requires signatures from Alice and Bob. Well, Bob can add his own signature to this. So Bob knows, well, with this transaction, I'm capable of accessing this 0.01 millibitcoin. So for Bob, this is sufficient to receiving this one is sufficient as accepting a payment. She no longer needs Alice in order to access 0.01 millibitcoin. Now, if Alice wants to do another microtransaction to Bob, she can just repeat that and make another version of this, where the balance is shifted even more towards Bob. And again, Bob, from this point on, Bob knows he has access to 0.02 millibitcoin, so he can accept that as a payment. So in the end, after 80 minutes, the balance of Bob is 0.8, the balance of Alice is 0.2. Now, if Alice stops using the Wi-Fi service, what Bob can do is Bob can add his own signature and publish it on the blockchain. So that makes these balances definitive. It can no longer be changed. So this closes the microtransaction channel. Now, there's one thing we haven't dealt with yet, and that is while the transaction channel is open, Alice is still able to add her own signature to this very first one that was signed by Bob. So what she could do is first use Bob's Wi-Fi service for a while, and then suddenly she spends this one, and if she's lucky, it gets accepted into the blockchain, and then she gets all her money back. So that's not good for Bob. We want to prevent that. And the way to prevent that is with a feature in Bitcoin that is called a lock time. And basically, a lock time can be added to a transaction, and the lock time says, well, this transaction is invalid until a certain point in time. And the effect of that lock time is that before that lock time, it is safe for Bob, because Bob can always publish one of these, and he will be faster than Alice, because Alice has to wait for this lock time. The downside of this solution is that this type of microtransaction channel has a limited lifetime, because Bob has to publish one of these before the lock time expires. Otherwise, it becomes unsafe for Bob, because after the lock time expires, Alice can publish this one. But, well, except for the disadvantage, it is a system that is safe for both of them. Now, what did we accomplish with this? The fun thing is only two transactions end up in the blockchain. That is this one and this one. So we only have two transactions in the blockchain, but in between there could have been millions of microtransactions going on from Alice to Bob, and none of them has to end up in the blockchain, but all of them are secure. Alice and Bob do not have to trust each other in order to make these payments. So, any questions so far?
Incidentally, in case you're running a credit, this scheme is Jeremy Scoman's.
Okay, not my current.
Yeah.
No, okay. My current was the one who implemented it first, then, or
Actually,
make much.
Carlo implemented it first.
Okay, it's just the noisiest. My current. Okay, that's how things often happen.
My current did initial proposal, but it was very broken. Jeremy Scoman went to fix it.
Okay.
Adding the extra steps there.
Okay, thanks for the info.
I have one question. With this payment channel, is it also possible for Bob to pay Alice, or does that not work?
No, we'll come to that later. So this is just for unidirectional from Alice to Bob. Okay, well, let's continue. Okay, continuing with the bidirectional example. Suppose we don't have a service provider, but we have a Bitcoin exchange. And with a Bitcoin exchange, typically sometimes you want to buy and sometimes you want to sell. So you want to have payments in both directions. Now, the customer cannot really trust the Bitcoin exchange. There are a couple of historical examples for that. Usually the exchange cannot trust the customer either, because, well, there are so many customers and you cannot check all of them. You have the same situation that both parties cannot trust each other but still want to do business. The customer does not want to have too many Bitcoins stored on the exchange. So you want to send as late as possible your funds. So you want to be able to send your funds quickly. So preferably without having to wait for confirmations. I think this is another use case for microtransaction channels. So what if we applied the previous design of the microtransaction channel to this example? So we have the same thing here. This is initially Alice owns 10 Bitcoins. Then this is deposit transaction. So it sends it to an output that requires 2 signatures. Then we have the initial withdrawal transaction that requires the lock time. And then if Alice sends 3 Bitcoins to Bob, we have this updated transaction. Now, what if we want to do a transaction in the opposite direction? So obviously the balances have to change to something like this if 2 Bitcoins are sent back to Alice. Now, can we make this secure? Let's see. First of all, Alice has to be able to access the increased amount of funds. So Bob has to give Alice his signature. So the signature has to be Bob's signature here. Now, another problem for Alice is, she can receive this, but Bob can still spend this one immediately. So, and Bob has an interest in spending this one because this one gives Bob a larger number of Bitcoins. So there is an interest and an opportunity for Bob to cheat in this system by publishing an older version of this transaction. How can we prevent that? Well, actually, the problem is very similar to the problem of the previous design that was solved with the lock time. So there was someone I think it was somewhere in 2012, 2013, somebody came up with a solution for this. That is, well, if it's the same problem, let's use the same solution. So we add lock times to the other transactions. And the idea is to decrease the lock times on updates. So, and the idea is this transaction can be spent before this one can be spent, and this one can be spent before this one can be spent. So that means that the latest version is always the first that can be spent, and that makes sure that gives you a guarantee against somebody cheating by spending an earlier version. Now, this gives you a disadvantage, of course, because, well, I told you the log time gives you a limited lifetime of the channel, and now we make it worse because the lifetime is not only limited, but it is decreasing. Every time you use it, you have to decrease that log time. Now you don't have to decrease it every time, but you only have to decrease it every time you reverse the order, you reverse the direction of payments, but still it's quite a disadvantage to this design. Questions so far? No? Here?
I remember you reminded me that you are of the opinion that you shouldn't use time, but something else in the hash log time. Isn't that it? Look at it, you know something.
Don't remember
that you shouldn't depend on time, but on signatures or.
I don't remember what I emailed you.
No, that's not important.
Something that might correspond to that is these log times. They can be specified in two different ways. Mm-hmm. One is as a timestamp. So mm-hmm. let's say a certain date and a certain time of the day. Mm-hmm. And the other way is to specify a block number. So these blocks form a chain in Bitcoin, and you can specify, well, it is invalid until that point in the blockchain. Mm-hmm. And these have slightly different characteristics. I don't know exactly which is better, but yeah, in actual implementations you have to think about that, of course. Mm-hmm. So let's have a little bit more detailed look at these log times. There is in a Bitcoin transaction, there are two different time-related things. One is the log time that says, well, this transaction is invalid until a certain point in time. And the other thing is the sequence numbers in the inputs. Now, these sequence numbers were originally intended for something else, but that original feature that was never going to work. People didn't really think about that, I suppose. And recently, people came up with an alternative way of using these sequence numbers. And this new meaning that is being assigned to these sequence numbers is to let the sequence number specify a relative point in time, where until that point in time the transaction is invalid. And it is relative with respect to the point in time where the parent transaction is included in the blockchain. So at the point that the parent transaction is included, sort of a clock starts ticking, and only after a certain amount of time or a certain number of blocks, this transaction becomes valid. That is what you can specify with the sequence numbers. So you have both an absolute and a relative measure of time in Bitcoin transactions. Now there are some other new features that are being added. I don't know the exact status at this moment, but there are script operations that can be added to the scripts here. And if check log time verify is executed, it checks whether the log time in the spending transaction has a certain value. And if it does not have that certain value, then the script evaluates to false and it makes this transaction invalid. And similar, if a check sequence verify operation is executed, it checks whether the sequence number has a certain value. And if it does not have that certain value, it counts this transaction as invalid. So using these instructions, you can already specify relative and absolute log times in these transactions. And that turns out to be quite useful. To give one simple example of check log time verify, here we have the original channel design for the Wi-Fi example. Now, if we use check log time verify, we could change it into something like this. We have an output script here, and the output script says, well, you can spend it in two different ways. One way is Alice can spend it, but then she has to wait for a relative log time because there's a check log time verify instruction here. And the other way is Alice and Bob can spend it together, so when both of their signatures are present. And with this output script, Alice can create this transaction with the log time, and she no longer needs Bob's signature on this transaction, because she can use the first clause of the contract, so to say. And she only needs her own signature on this one. So that is a sort of a simplification of the protocol. You no longer have to send this transaction first to Bob and then get the signature back. And I think for this specific design, it also solves you no longer need a solution for the transaction malleability problem, but that's a bit off topic, I think. And for the other ones, they still make use of the clause where both signatures are needed. So this is just for this specific design, it's just a minor improvement. But let's look to at this design. This is a design of an unlimited lifetime microtransaction channel. So until this point, all these transaction channels had a log time that limited the lifetime of the channel. But with this design, the lifetime is no longer a problem. Now, you can already see here, it becomes more complicated. Instead of one transaction, the state of the channel is determined by two transactions. And these two transactions are completely symmetrical. So if you swap A and B, this one is basically the same as this one. And what you see here, there is a balance for Alice and a balance for Bob. Now, these ones do not have a log time, but there is a check sequence verify instruction in the output. So what happens? Let's suppose that Alice wants to close the transaction, the microtransaction channel, and we have these two. Well, this one has Bob's signature, so the only way that Alice can close it is by adding her own signature to this one and publishing this on the blockchain. Well, what happens then? If Alice does that, Bob can immediately access his own part of the channel. So this output is immediately spendable. But this output has a more complicated script. So if Alice does that, Alice will be able to access these 8 bitcoins, but she has to wait for the log time. And she has to include this blockchain, this log time, because it is required by the check sequence verify instruction here. And the fun thing about this log time is it uses the sequence number, so it is a relative log time. The clock for that only starts ticking when this one is published on the Bitcoin network, or when it gets included in the blockchain. So as long as you don't do that, as long as you don't close the channel, the clock doesn't start ticking yet. So as long as you don't do that, the channel can stay open forever. Now, the question is, of course, is this secure, this type of channel? What if you do some microtransactions from Alice to Bob? So the balance changes. And now we want to prevent them from using an old version of these closed transactions. Now, what would happen if Alice does use this old transaction? And that is where the second part of the script kicks in, because the thing is, there is a second clause that allows Bob to spend this output as well, but only if he has a value called RA. So that's just a secret piece of data, and the hash of that data is included in this script. So in order to spend this output, Bob has to provide his own signature and that secret piece of data. Now, initially, Bob is not able to do that because he doesn't have that piece of data. It is a piece of data that is generated by Alice, and initially it's only known to Alice. But when we update the channel, the rule of this channel design is that Alice has to provide this value to Bob. And otherwise Bob will simply not accept that as a payment. So Bob can see that he has this value RA. Now what can Bob do with that value? Suppose that Alice decides to try to cheat by publishing this one on the blockchain. Well, Alice can spend that output, but she has to wait for the relative lock time. But Bob can spend it immediately because now he has this RA value and he can add his own signature. So Bob is faster than Alice because Bob does not have to wait for the relative lock time. So that means if Alice tries to cheat, then Alice risks losing everything because the entire contents of the microtransaction channel becomes available to Bob if Alice tries to cheat. Of course, if Bob is ultra honest, he can also send Alice's one Bitcoin to Alice. But then, well, there's absolutely no reason why Bob would have to do that. One thing to mention is you have to regularly check this channel. If you use it for a while, and you have to regularly check whether the other party has closed the channel. Because as soon as the other party closes the channel, the clock of this relative lock time starts ticking. So suppose that is a 30-day clock, then you have to check at least every 30 days whether the other person has done that, because before this 30 days expires, you have to claim the funds for yourself. So that is something to be aware of using this type of channel. But for the rest, this channel has an unlimited lifetime. Any questions so far?
So how do we check that the channel is open or closed?
What you do is you observe on the Bitcoin network whether this output is spent or not.
Okay.
So you can, I don't know how pruning nodes do that, but at least if you have a fill node, you can just query your database on whether there is a transaction that spends this output. And if so, then apparently the other person has performed a transaction that closes the channel.
Okay. Peter, do you have any clue on that?
That's really accurate. The tricky bit is, for SPV, there's no cryptographically proven reliable way to know whether or not a transaction has spent an input. Because your peers could obviously just refrain from telling you about transactions expended.
But do you know if a pruned node can?
Pruned, yes. Pruned
Yeah.
can do this.
So
Okay, well,
pruned node can check if it is spent.
Okay, okay. SPV, that's the thing that's important, whether SPV is able to do that or not. Yeah. And it's not exactly clear, but usually
I'd say they clearly can't without just having a copy of the blockchain. Sorry, to be exact, they could. An SPV node could, in theory, just download every block while the channel's open. Which isn't that much bandwidth.
Yeah, starting with the point where this transaction is included.
Yeah, 140 megabytes per day. It's not that bad.
Yeah, and when you keep your cell phone off for a couple of days, you turn it on and then it has to
Yeah.
keep track again. But
You can discard the blocks after.
you can discard the blocks if they don't contain anything that spends this output. Yeah, it's possible.
I have a question about because you say you use the check sequence verify and it checks the log time. And that part I didn't understand because I thought there was a check the log time verify and check sequence verify.
Yeah, check sequence verify checks the sequence number. But the new meaning of the sequence number is that it acts as a sort of a relative log time. So, so with this green symbol, I mean that this one has a sequence number that includes a log time limitation.
And the sequence number is like number of seconds or something, or timestamp, or?
I think it also has both ways of specifying the
relative
either block numbers or
block time.
Okay, right.
And it's basically up to, I believe, roughly a year for either, a year worth of blocks or a year worth of time.
I missed a little bit the part how the exchange of the RA number is done. So in notes there was
when Alice, when the updated, when the state of the microtransaction channel is updated, Alice has to send this RA value to Bob, and correspondingly here there is an RB value, and Bob has to send that RB value to Alice. If Bob does not receive this RA value, or if it is somehow if somehow it does not correspond to the hash specified here, then Bob simply does not accept that as a payment. You can just say, well, you're trying to do a bogus update of the channel. So they are sent when updating the state. And I think you first have to make sure that you get an updated transaction here before you transfer the RA value. Otherwise, you can end up with a situation where the old state becomes insecure, but the new state is not ready yet.
And when Bob doesn't accept it, he simply doesn't sign the new transaction.
No, I think you first have to sign these, but Bob simply does not accept it as a payment yet. So if there's some service in exchange for this payment, Bob simply does not deliver the service yet. So, like that, there has to be some point in time where they agree that the payment is taking place. And Bob only accepts it as a payment if this RA value is also sent. Okay.
So the scaling problem has been solved now.
Well, let's continue with the next slide. I think we'll come to that quite soon. So let's go to the Lightning Network, or my own piece of software, Amico Pay, and I won't go into the details of the differences. They're so much the same that all of this applies to both. If you want to be able to do payments to everybody on the world, and you want to be able to receive payments from everybody, then if you use microtransaction channels, you need about 7 billion channels, right? And everybody else needs 7 billion channels. So in terms of scalability, I mean, that's why I continue here. In terms of scalability, that looks pretty bad. So the solution for that is to make a sort of an internet of micro transaction channels. And every single person or organization may only have just a few microtransaction channels, but you're still able to reach the entire world through the network by indirect payments. So you pay to your next neighbor, and the next neighbor pays the same amount to the next neighbor, and so on, until it reaches the person who is supposed to receive the payment. So each of those links is one microtransaction channel. Now the problem with this setup is, of course, that there are middlemen in this system, and well, you don't want to have to trust these middlemen, because, well, especially for the innermost ones, you don't even know them. You have never chosen to do business with them. You don't want to accept any risk there. And what they might be able to do is just stop the payment over there. So you pay this person pays this person, and this person says, hey, nice, money, I keep it. And this the person who is supposed to receive it never receives it. So this is theft, right? We want to be able, we want to prevent this. And the way we do that is that the person who is supposed to receive the money creates a secret token. That's basically just a piece of random data. Initially, he keeps it secret from everyone else. And he just calculates a secure hash of that token, and the hash gets distributed across the other participants. Now, these participants make agreements amongst each other. And these agreements, they say, well, here is the hash value. If the corresponding token can be demonstrated before a certain timeout, then the transaction continues. And if that is not the case, the transaction is cancelled. Now, this is not just a contract, but this can actually be expressed in terms of a Bitcoin script, so that it is actually enforceable. And this is called a hash time locked contract, where you have a...
This was what I was asking about. You weren't happy with the fact that they were using, in the universal payment channels, that they were using, dat heeft vervelende consequenties als je transacties over meerdere hops in een netwerk stuurt. Ja, goed, maakt het eigenlijk niet uit.
Okay.
Yeah,
I was replying.
Ze zijn de time-out van de microtransacties vergeten.
Yeah, they forgot the timeout, I think.
Yeah.
There was a certain paper about something, a certain generalized concept of this sort of networks. But in that paper, they forgot to add the timeout. And what happens if you forget this timeout? Then, well, you lock your payment amount in the channels, and then the person here can hold all these amounts ransom, right? You can just say, well, nobody will be able to access their funds. They will not be sent back. They will not be sent forward. And he can just demand, well, I want 50% of that or something like that. And so that's an uncomfortable situation. So because of that, you have these timeouts, and these timeouts are different on all these different links. And the reason is for that is you want to give the people in the middle some time between the timeout where they have to pay and the timeout where they are able to receive to sort of forward the secret value. So each of them has a slightly different timeout, but in every individual link you have this hash timeout contract that specifies the hash of the secret token and the timeout value. And basically the script sort of evaluates this expression. If a certain amount of funds is locked for a Lightning transaction from Alice to Bob, then it says, well, that funds can be redeemed by Alice, but only after a certain lock time expires. Or it can be accessed by Bob, but then he has to show the secret data. So this way, before the timeout, Bob is able to access his funds with the secret data. And by doing so, he reveals the secret data, and Alice can use that to forward it upstream. And after the timeout, Alice is able to get the money back. And in that case, the transaction is cancelled. Now you can combine this with the unlimited lifetime channel design. And actually, by combining them, the output conditions become a little bit complicated. But if you think these away, it's exactly the same as the unlimited lifetime channel design. And so the only thing is these and these scripts. And what it says, this is for a payment from Alice to Bob. So it says Bob can access it if he shows the secret data, Alice can access it if the lock time of the contract expires and the relative lock time of the channel expires. And Bob can also spend it if he has the RA value of the channel. So this last clause is of course only applicable if Alice tries to cheat, similar to this one. So it's a nice puzzle to make this kind of scripts and try out all the possibilities of things. Yeah, maybe you can try to figure out for yourself if you find any way that this can be exploited. A bit of an unfortunate thing I discovered about this type of design is the interaction between the check sequence verify and the check log time verify. So the log time for the microtransaction is an absolute number, and the check sequence verify for the channel is a relative one. But actually the requirements are such, I think, that the log time has to specify a longer amount of time than the check sequence verify, and that is a bit bad because you want to have the check sequence verify. You want to have that quite long, so that you don't have to check every day whether the other person has closed the channel. And actually, you want the check log time verifier to be quite short because that gives you fast confirmation about whether the transaction is definitive or not. So it is a bit unfortunate that the log time of the hash time log contract has to be longer than the sequence verifier of the channel. This channel design, this is proposed by Rusty Russell for his seed lightning implementation. I think Joseph and Tej originally proposed a slightly different channel design. One of the things is they were using private key exchange instead of these hash values. Well, I don't think that adds many advantages, but they were also using some other methods of invalidating old versions of these transactions. And actually their design did not have this problematic trade-off, but it depends on adding certain features to Bitcoin.
No, sorry.
Yeah. Yeah, I think it has to do with certain sig hash flags that they want to add. I sort of forgot all the details about that, but basically there are a couple of variations on this design.
You're probably thinking the sig hash no input flow if they want.
Yes.
Does replace by fee have any implications for this?
If it does, it's insecure.
I think it doesn't. No. It's
Anything that the fee is already determined up front, I guess, when you open the channel.
Yes. One of the things you have to be sure about in this design is that you have to be sure that you are capable of spending these transactions that you are making. So probably you want to make these fees quite high so that you're sure that they will end up in the blockchain even when the block size limit is continuously reached.
You can add extra inputs to a transaction after the fact.
Add extra inputs to transactions,
yeah,
even when the signatures are already present.
Yeah, if you sign with the Zcash and you want to pay.
Oh, yeah, so that might be an option. Yeah.
Now that may interact badly with assuming SafeWeb fixes malleability in some cases, but for this case, I don't think that would be true.
No, in normal cases you only have one input, and Well, typically you add just one input.
Well, the transaction you care about is the last transaction you chain, right? That's the one you really want to be able to get in. As long as you add more inputs to that, you should be okay.
Yeah, because you have pay by child transaction or however you call it. Yeah.
And Peter, isn't it also that if I receive a transaction and it is done with replace by fee, then I can, as a receiver, I can see if it has been done by replace by fee?
Oh, yeah.
So in other words, if I can see that it is not being done with replace by fee, I know that I don't have to be afraid that it suddenly gets to someone else. So.
Well, I'd say you do have to be afraid. Zero counts doesn't work very well.
Yeah, okay.
But the converse, where you might be afraid that you weren't able to replace it, is certainly true. You know, you can be sure that yes, this transaction can be updated later. You know, which can be useful.
You could get some sort of fee war, I guess, if Bob, it's just like 10 Bitcoins in one channel and Bob wants to use an old transaction and he adds like two Bitcoin fee. And hopefully the miners will see that and not.
So we are in this scenario where this is an old state of the channel.
And then to incentivize the miners to ignore the lock time or to just wait out the lock time basically.
So you incentivize, you put a huge fee on this one and hope that the miners will ignore this lock time, ignore these transactions because they know they will get a huge fee on this one.
Yeah.
You know, that's a bad scenario.
Slightly,
Yeah, I mean, I think that's a fundamental problem with a lot of this stuff. Well, on the other hand, of course, you can respond to doing that by adding your own fee to it.
Yeah, that's why I said fee war, but yeah. I guess for a miner it's always a gamble because it's only like a 1 in 10 chance of getting it anyway. But,
That's not a good thing.
I had two questions in particular order. One of them is like, I forgot, we dive into this stuff, but I forgot what was the incentive of the intermediaries, the middlemen, to, of course they need to,
Do not steal it.
no, not steal it, but to facilitate the transaction.
Well, presumably you can
And also,
give
sorry, question 2 is, how can you prevent the middleman sending the transaction 2 times around the world? And is finding the most efficient path, the most cheapest path. How can Alice in this case say, I want to take this path, or does the middleman decides this?
So the simplest way of looking at incentives for the middleman is to add a small transaction fee for forwarding the transaction. The question is, of course, who decides the transaction fee and how are you going to negotiate that? There are different ways to look at these fees. One of them is that these parties, if they have a rough map of the network, they can decide their own routes. So they can ask for nodes, well, what are your routes and what are your fees? And they can choose for themselves, well, this is the fastest route or the cheapest route. And I'm going to use that for my payments. Another possibility is if you don't explicitly let the endpoints pay for the fees of the middleman, but just let them pay for the fees for the direct neighbor. I mean, that's usually what we do with the internet, right? I'm not paying the Amsterdam Internet Exchange. I'm paying my local internet provider. And my local internet provider might pay something to upstream or downstream providers.
That was something I was also wondering about, that this stuff won't really centralized by just getting huge hubs with a lot of capital available and say, all right, we have the lowest amount of fee because we can facilitate a lot of transactions in a day and earn little kits of fee, but we can do that because we have a lot of money available to lend for the whole.
Well, keep in mind, I mean, you've got to, decentralization for decentralization's sake doesn't necessarily make any sense. You gotta ask, like, what are you actually trying to prevent from happening? And in a scenario where those big centralized hubs still can't steal their money, having a pile of transactions go through one hub isn't necessarily all that bad. You know, and equally, I mean, in terms of like DOS attacks, where they just stop allowing transactions to be processed, that's a reasonably easy to understand risk. It's not necessarily a good thing if they tie up a lot of capital, but this is a relatively known risk, and it's also one that apparent decentralization doesn't necessarily help either. If you really care about decentralization and go for smaller hubs, I mean, how do you actually know those smaller hubs are actually independent? The important thing is to just not have this vulnerability in the first place, regardless of whether they're centralized or decentralized.
Decentralization doesn't fix it, but it's a bit of a religion.
Yeah. Decentralization has simple properties, and you got to ask if the properties are worth the cost.
So these middle nodes, they cannot steal from you, but they might be able to block payments from going through themselves. In that scenario, well, a relatively straightforward solution is, if I cannot pay through this route, I set up a new microtransaction channel directly towards the endpoint, because apparently we are on two sides of the network that are not properly connected.
Well, why can't, isn't, like Peter was saying, we were talking about these federated solutions earlier. If you've got a situation like that, why can't you just have a network that has a rule in it that has can't see what's actually going through the channel?
Well, that's
subscribe to that.
That's what I'm trying to do in Amico Pay.
Yeah.
The thing is, with this is a network where you do routing, right? You go from one point
And it's
to
been
another
done
point.
before in many other P2P networks.
So the point where you are routing towards has to have an address. I mean, otherwise you cannot route towards a certain point.
It's got gossip algorithms and all sorts of ways you can do things like that, but you don't, from node to node and ask a question.
Yeah. What I do in Amico Pay is I decouple the task of being an address and the task of being an endpoint, either endpoint of the transaction. So you can be both an endpoint and have the address, or you can be an endpoint without an address or without using your address for the transaction, and you route from both sides towards a node in the middle that has an address.
The nodes can even contain address information of other nodes and route to known nodes in the network.
And the fun thing is, if you don't have an address, people don't know who you are. So they know, well, there is an incoming transaction over this link, but I don't know who it is. I can only see it's coming from that direction.
Is there also something possible where you send, to achieve one transaction, you just send 10 or 20 differentiated through the network, and the first one that arrives is the geldige, the right one, and the other one, so the intermediate hubs have an incentive to do their job right, if they want to receive a little bit of fee.
It's a lot of traffic.
Yes, and you can do it sequentially, right? I mean, you can try one route, and if it fails, you can try another route, and so on. These transactions are quite fast because you don't have to wait for confirmations.
Yeah, because we are now talking about micro or nanoseconds in this whole story.
You are talking about ping times.
Yeah.
So ping time is the time it takes you to transfer your bytes from one place in the internet to another place in the internet. Now, if you, in the worst case scenario, you go from here to Australia, back to here, back to Australia, back to here. And that's the longest distance, right? So you have the longest ping time. And you have that maybe about 10 times. So I think typically it's half a second or 1 second, worst case. That's one transaction attempt.
Okay.
So if you're having connection problems, you can try it a couple of times over different routes.
And I was also wondering, sorry, do you have a question?
Yeah, I have a question. It's a little bit different than some maybe
No, I have a more generic one, so please go.
Okay, yeah. I have a question about the hash, because it's a hash locked contract you said. But,
Yes.
I had some trouble finding it in the transaction. On the next sheet you showed the complete
Here?
transaction script. So where is the actual hash of the random secret that Bob made? How does it? Or is it separate?
Here I say you need R and you need a signature for B. But actually what's included in this script is not the R value itself, because that's secret. What is included here is the hash of R.
Okay. All right, and it's different from array. Array is the one you provide on the next step in the channel.
Yes, exactly. So if you see it, I have a couple of, I've written out how they should look as Bitcoin scripts. So R and B looks like, well, here's the hash of R, and you check whether a certain input is equal to that. That's what it's probably will look like in a Bitcoin script.
And you have to make a new one every time you update the channel, or is it?
These R values are unique for microtransactions. So every time you make a new microtransaction, the receiver of that microtransaction has to make a new R value.
Okay, yeah. Okay.
Yeah, my question is that, I mean, I'm not a programmer, so by definition it's more difficult for me. But I mean, I've seen your presentation, I guess 6 times now, and I still have not.
This one is only the second time.
Yeah, but I mean, in general, the Lightning Network stuff, and I still have problems because it's so, complicated, interdependent, and whatever. And so I was wondering, I'm now reading about the smart contract stuff and about the contract, and about the criticism to it. And I mean, these are actually smart contracts, if I'm right.
Yes.
So I mean, could I compare it? Because I can imagine that there are really, really a lot of stuff that can go wrong in all these things. That you really have to check if all the apps work like they pretend to work and such.
Yeah, you really have to check whether your design is solid, whether there's no escape in one of the possible.
Because I mean, Bitcoin, it also took me a while before I understood it, but once you understand it, the principle is very simple, and I mean, I can imagine that the biggest problem of the whole thing is that it's just that it's all very complicated in it, and that means in itself that
It's complicated.
and that's the biggest hurdle.
But the complication is in the protocol design. When that is finally figured out, then.
Yeah, but I mean, I can imagine that every new app you write will always be extremely complicated, or not?
New app for this?
Well, you can make a library for making these kind of things and reuse that library in different applications.
Okay.
Yeah, but it's the same thing as with cryptography. If you want to re-implement SSL, that is a lot of things you can do wrong there.
Yeah.
And most people don't do that. They use a standard library for SSL.
No, but I just mean, it's there are so many things. Oh, this can go wrong.
Welcome to crypto.
And the way Joseph told me he looks at this is as a circuit. It's a circuit for making sure that not electric currents go to the right direction, but that funds go to the right direction.
Okay.
And it's a way of looking at these things. You build a circuit out of different Bitcoin transactions.
That's why it's called Lightning.
It's called Lightning, I think.
Circuit is going to be.
It's called Lightning because this bears some similarity to the way how a lightning strike forms in the air between the cloud and the ground.
Okay.
Do you have any thoughts on the Thunder network, which is going to
running parallel to this?
The only thing I know about that is that, well, according to my knowledge, it is just one of the implementations of the Lightning Network that is currently in development. I don't know anything more about it.
It's like 4 different versions in the works now, I think.
Yes, I counted at least 5 projects of varying activity. So there's Seed Lightning from Rusty Russell, written in C. Then there is the project of Joseph and Tex, which is written in Go. Then there's AmicoPay from me, written in Python. Then there's this project, I think that is Thunder project, that is written in Java. And there is someone in France writing something in one of these functional languages.
That was the French language.
Would you call that a functional language? Okay, so there are at least 5 projects, and I'm quite certain that, well, at least a couple of them will eventually become available.
Rusty is making some cheeky jokes about you.
About me?
Yeah. He says, it's an exciting area and his insights should be enlightening. So,
Didn't he create the website?
it's the value job.
Is it about me or what is it?
Yeah, but I mean, it wasn't really a joke, but I see it in writing.
Okay.
I think hey, that's a cheeky one.
Enlightening.
So,
So wasn't Lightning already like deployed on testnet? Not deployed on testnet, but the opcodes that were required for Lightning to work.
These opcodes were already deployed on a sidechain.
Okay. Yes.
So now I don't know. Maybe you know more about that, about the status of sidechains themselves.
Well,
Yeah.
the opcodes are being deployed on the SegWit testing.
Yes, but for sidechains to be completely secure, you needed a soft fork in the main chain.
No,
No?
you can't make them secure.
You cannot make sidechains secure. Okay.
You either trust centralized federated entities or any other trust miners. So I would be surprised to ever get implemented on Bitcoin mainnet.
Okay.
so just to be clear, in your opinion, there cannot be trustless sidechains.
Not with currently available tech.
Okay.
With like really fancy recursive snarks, which is just magic voodoo math.
Mhm.
Yeah, you could, but that's really way off.
I'm certain that
Once you do
Ethereum
that-
can do that.
Once you do, the thing is, once you do that kind of math, you don't need sidechains.
Yeah, because Paul Storch, he had a video out last week, and he was actually, if I'm right, please correct me if I'm wrong, he was saying that he wanted the miners to be involved, but as far as I know, he was thinking of a kind of a trustless kind of solution. Am I right?
Yeah, I don't remember details. Okay.
I think his idea of trustless is not what I would have my idea of trustless to be.
Okay.
He's, basing this very heavily on economic assumptions, I would think. Similarly, like a lot of people would go and be of the opinion that merge point sidechains are secure because of their economic assumptions, but I don't think those are reasonable assumptions.
Peter, can I ask you, do the other Bitcoin core developers like this and the blockstream guys disagree with you on the security side?
Oh, yeah.
Okay,
I
so
mean, they wouldn't be working on it if they agreed with me.
Adam and Greg Maxwell would say that they are secure.
Especially, I think, Greg, but I don't think they're right. I think they have rather odd assumptions. Yeah, like today's example, Mark Friedenbach's written most of this, where his assumptions seem to be essentially that there will be an economic incentive to keep mining the sidechain, and that is sufficient to mine it honestly. Whereas the argument I would make is you can't assume, you can't assume everyone has the same kind of incentives.
Okay, but the jury is out in a sense.
Well, in the sense that nobody's actually influenced one, but by that, by that standard, I mean, you could say that the jury's out for whether or not block size increases, centralized things. I think based on principles, I think it should be obvious. Side chains are very insecure right now for the merge line versions. But, people disagree on that.
You are donating some, or?
Try to.
It's the only purpose.
QR code too far away.
That's too far away.
It's quite remarkable that it's still very difficult to photograph QR codes.
Maybe we should take a picture and then scan the picture. Depends on the library. I'm not sure.
Yeah.
Last month we scanned one from an Atari 8-bit.
Oh, okay. In QR code library.
No, QR code.
According to the stuff you're working on, it's the library piece.
Well, basically, yes. AmicoPay is a sort of a library and framework for Lightning software. So it provides a programming interface for applications, for instance, user interfaces. And on the other side, it allows you to add plugins for instance, for different designs of these microtransaction channels. Over the years of AmicoPay development, I experienced that especially the design of these microtransaction channels has undergone some changes. So I just wanted to be able to update that in the AmicoPay software. So right now, AmicoPay is just a sort of a framework that does all the routing, and I have some very simple plugins for microtransaction channels. The actual microtransaction channel that I described here still has to be implemented. It is not present yet, but eventually I will add that. Yeah. Cool.
I'm still wondering how pathfinding exactly works. So
right now in AmicoPay it is extremely stupid. Right now, it tries every possible route, and the only thing it prevents is recursing into an endless loop. That's the only thing it's not doing.
Well, it can't be any worse than the alternative.
Yes.
Yeah, I was also wondering, isn't there an incentive for every participant in the network to route as much as possible because they improve their own network?
How would that improve their own network?
Because it's like if the more you help others, the more knowledge you get about the network, and so yeah.
I see it as very similar to the internet. I don't see internet providers doing unnecessary routing. Unless in certain cases, they might do it for political reasons. I mean, if you're in China and you do an internet connection to Europe or America, there might be some strange things going on. But in general, I don't see that happening. And the reason I think is because there are fees attached to forming extra hops, and because the capacity of these channels is limited. I mean, with internet connections, that's the main reason that they don't perform extra routing, right? It's because the capacity, communication capacity of cables is limited, so they don't want to use more than they need of that capacity. Well, in Lightning, the capacity is also restricted because every channel has this balance, and you cannot exceed the maximum balance of the channel. So what you might want to do is optimally you want to have the balance of the channel somewhere in the middle, right? That both parties have approximately half of the channel capacity. Because in that way you can do transactions in both directions
So just to have it clear for me,
Yeah.
if I'm part of the network, I don't have an unlimited coin bandwidth, to say it like that.
No, you don't.
Because otherwise my channel gets flocked, or how you call it.
It is of course normal. You cannot spend more bitcoins than you have.
Yeah.
Because in a trustless system you cannot have debts.
Yeah.
So you cannot spend more than you have.
Yeah.
But the same is true for the next hop. So if you are only connected to one node, it's also true you cannot spend more than the other node has in his channels. Because he has to be able to forward your amount to the next hop.
So if I have a 2 Bitcoin channel with you, then and I want to send something to Janus, then you have to have a 2 Bitcoin channel with him.
Yes, and I have to have 2 Bitcoins in that channel. I mean, if it is a 2 Bitcoin channel, but Janus has the 2 Bitcoins, I cannot send 2 more Bitcoins to Janus.
If you have a 3 Bitcoin channel with Janus, then my 2 Bitcoin channel with you cannot, at least not go through the 3 Bitcoin channel.
Well, only if I have 2 of these 3 Bitcoins on our channel.
Okay,
yeah. Because that's the only way. That's the only way that I can.
So it's really like physical cash in the sense that yesterday Peter, I and Michiel had some kind of a small lightning network in real time. Because I wanted to be paid in Bitcoin, you wanted to get euros, and Michiel just wanted to have money or something. And it was really complicated, but then it's something like that in the sense that I give you 2 euros and and
Can I ask you something? Because we're talking about centralization and decentralization, and sometimes it's about the shifting point. To what extent is what the goal that you're trying to chase of integrity of the process and actually working complicated by this quest for a lot of decentralization? And like Peter said before, you add a centralized component in there, it's not unless it might actually help the model. Is that a factor that because you feel compelled, the whole movement around Lightning is all compelled on this decentralized thing? Yes or no? It's like, is that a factor?
Well, I think centralization and especially bad consequences of centralization that could possibly occur. They are a factor that is being considered in the design of.
What about good consequences of centralization?
Good consequences of centralization.
Some decentralization.
Yeah.
Bitcoin being the world dominant currency.
No, I'm just really going back to what Peter said before, by adding a centralized component, you can actually maybe add some certainty into the selection of nodes or addressing or whatever. And
or
suddenly
it just might work.
It just might start to make it work.
Yeah.
It isn't necessarily a bad thing.
And also, let's go back to like the whole P2P movement happened before Bitcoin. A lot of those networks on the App Store was a hybrid P2P that had a very central component. Okay. Then it got more and more decentralized to a bit but somewhere in the middle. Some of those networks that worked had a very effective P2P decentralized part, but also some centralized components, and that there's a balance struck there.
Yeah.
And so in the realm of this, is half your problem that you keep on wanting to make it as decentralized as possible, like as if it's a religion, or is there a point where some centralized things can actually achieve the greater good?
Yeah. Well, the thing is, with many of these decentralized networks, you can sort of experiment and try to get things right. And when it is too centralized, you just replace a part and make it more decentralized. Or if you cannot solve something in a decentralized way, you can just just put a centralized part in that. But in this case, I think one of the things you have to be careful with is network effects. If you design a system from the beginning in a certain way, it can become really hard to change it afterwards. if it turns out that there is a need to change it.
Well, but why network effects are usually positive for networks?
It is positive for the existing network.
Yeah.
It is negative for any competitor of the existing network.
Yes.
So if you have an established network and you think, well, okay, this is not going right, we would like to change something, then, well, certain changes can be done inside the existing network, but for certain changes, you have to make an incompatible change. And if you make an incompatible change, then you have to create a new network that has to compete with this big existing network.
I don't think you really answered my question though.
Well, the reason that I mention network effects here is if your existing network is somehow wrong, you didn't think about something, and it is developing down the wrong path, it can become hard to fix.
Yeah.
So the reason that we are a bit afraid of decentralization, of centralization things, is if we are not careful about this and forget some very large centralization force, and if that turns out to have bad consequences, it might be hard to fix it. So we try to be careful from the very start.
So otherwise, in other words, once launched, it cannot be easily. It's like a satellite.
It's like
Bitcoin.
Yeah. Yeah.
Once it's out there, once it's grown big, it's hard to change.
And Bitcoin is supposed to be hard to change.
Yeah.
I mean, we are supposed to be. These rules of the Bitcoin network are supposed to be reliable towards the customers. So it is designed to be hard to change, and that is what we are running into with this whole scaling Bitcoin and hard fork discussion. Is well, at least a part of the community wants to change the rules, and it turns out it is deliberately designed to resist these kind of changes.
Now maybe especially with in the example of the 1, 2, 3, 4 steps, if we want to send from person left to person right to Bitcoin, to open payment channel for it work to Bitcoin, how much money is locked in total? Is it 4 times 2 Bitcoin or just 2 Bitcoin?
Well, I heard two things in your question that don't add up. You're saying opening a new channel, and you say performing a microtransaction. These are two different things.
Okay. Yeah, but when
No, but in this, I think what he means in this situation, you have 3 hops, so you have 4 micro channels. If you want to put 2 bitcoins through that channel, there is 8 bitcoins locked in total, because there is 4 channels that are locking 2 bitcoins.
Yes. So if you have a microtransaction going on from here to here, and it is you want to transfer 2 bitcoins from this person to this person, then you lock up those 2 bitcoins in this channel, and you lock 2 bitcoins in this channel, and in this channel, and in this channel. So that is 4 times 2 is 8 bitcoins that are locked.
So you have limited cash flow.
But the transaction takes 1 second, and after the second, all the coins in the middle are free to go.
Well, the channel is then the channel needs to close. But if the channel
No. Microtransaction just takes maybe 1 second, probably less than a second. And after the microtransaction is finished, the channels are not closed. The channels are just have an updated state.
As long as the channels remain open, the Bitcoin remains locked.
No.
The deposit remains locked.
But they can move,
Yeah, they stay locked inside the channel, but they can be used for other microtransactions.
They can use for other microtransactions.
It's locked in Bitcoin. But not
if you want to have a channel like this for 2 Bitcoin, you're locking 8 Bitcoin. Yeah. And that remains locked. You can reuse it, but you have 8. The more hops you have, the more Bitcoins you need to lock, and the more channels you're creating overall, you're locking up a lot of Bitcoins in those channels.
So you have a choice between either making Bitcoins available on the Lightning Network for payments or using them for regular Bitcoin transactions. If you have Bitcoins in a regular wallet, you have to lock them up in a payment channel to be able to use them on Lightning. And then when you want to use them in a regular transaction again, you have to close that channel
To
and
free them up.
get them back.
Put yourself as a network effect.
What do you mean with that?
Competing.
I mean, the more people have money locked up in Lightning, the less money they have available to spend any other way.
So it's ideally for holders, or hodlers, I should say.
Yeah.
Yeah.
I think typically the Lightning Network will be used for smaller transactions, and blockchain transactions will be used for larger transactions.
Yeah.
Because for larger transactions, these transaction fees don't matter that much anymore, and for smaller transactions, it matters less that these channels have a limited capacity.
Of course, it also might be that transactions going through third parties, they could care more about Lightning. Because, for instance, Coinbase, you might care a lot about a 10-cent transaction fee because your profit margin might be 20 cents. Whereas if I'm, sending money directly to any one of you guys, I'm sending the money directly and you're not going to care about that 10-cent transaction fee because I'm sending you $100. For Coinbase, it's different because the profit margin is so low.
Yeah, I think typically in retail, the profit they get is a very low margin of the products they sell. So when you get a little bit lower transaction fee, it can add up quite a lot to their profits.
And for instant transactions, another big advantage. Without no waiting for confirmations.
I think typically for smaller transactions, there's more need for faster transactions. I'm not sure about the whole high frequency trading market. I'm not too much into that. They might exchange billions in microseconds.
Yeah,
I'm not
normally
familiar.
for high frequency, this is even too slow, I guess.
Probably because these people really care about the speed of light, and they probably want to be able to just make transactions with just a single message, no backwards and forward going of messages. So if you're really into that, you might want to have a trusted system.
Direct connect.
If that works better for you, I mean, on average, your profit might be higher in a trusted system.
And some of those high-speed trading systems, they're so trusted that they don't use digital signatures because that's too slow. They just send a message around on a wire and hope that someone audits it after the fact.
Yeah.
Very, very little proof that anything actually happened.
Okay.
No questions anymore.
So when do you expect that we're going to see this in real life?
It's a hard guess because I'm most familiar with my own project, but I'm doing my own project in my spare time, and it's very variable what amount of spare time is available. And for the other projects, I don't have a very detailed view on their status, but as a very rough estimate, I think we have something like this somewhere next year, somewhere in 2017.
So how do we get you to quit the day job and work in full time?
We're trying to do that.
Money?
A lot of
Why hasn't Blockstream hired you yet?
Why hasn't Bitcoin hired you yet?
We tried.
Yeah, we have to find.
But I mean, for Bitonic, isn't it interesting for you to, besides blockchain info, to have Amico?
We tried.
But to have, to have Amico Pay.
It's very.
And I mean, in the beginning, it's more centralized, but I don't care because there isn't any other choice.
I think
but you should start talking again, I think.
I think so.
But especially for exchanges, it would be good to be some kind of hub in the Lightning Network and open up big channels with other exchanges and facilitating payment channels.
But I think for myself, the conditions of employment is something I really have to think about.
Since
I mean,
since when is your approval needed then? Sorry.
Yeah.
People will talk to Blockstream and work it out.
Yeah.
Yeah, they really
Yeah.
listen to people.
No, I mean, I don't care much about becoming rich, but I care about, well, being able to do this and about having some financial security. I mean, if I become rich upfront, that gives me some security, but that's not a very likely scenario. I mean, sure, be my guest, but
Just one other, because you're talking about Amico Pay, which is your own implementation, and there's other implementations, but these implementations are all compatible with each other, or are there slight differences there?
there is a proposal of a communication protocol as a sort of standard, but it is an unfinished protocol, at least last time I checked. And the problem I have in Amico Pay with implementing this protocol is it specifies the other parts, the part that I haven't finished yet. So the other, some of the other implementations start with developing the microtransaction channels, and I started with developing the routing and the node logistics and the architecture. And so these are opposite ends of the same problem, and they made a protocol proposal for their half, and I have a protocol for my half of the problem. And so
You're saying we're done.
right, almost done, I think.
Sounds like we should work together.
Some staples and.
I mean,
Together,
in
one right
terms
hand,
of
one done.
concepts, we are done. We know all the concepts we want to finish.
Well, there's pretty good coordination between most projects, right? Except maybe Thunder is a bit outside.
I think so.
Yeah, I just suddenly heard about Thunder, but did you already know about it?
I already knew about that project.
Oh, okay. So it wasn't a secret or something?
None of the published some stuff over there.
I think it was his bachelor project at university before he joined.
And who is his?
Thunder is from the German guy, is it? Mats Jella?
Sorry?
I don't know how you pronounce that. It's, yeah.
Something like it.
So,
Yeah.
Yeah.
Okay.
Shows you QR code again.
There's a message in there about Ethereum, by the way.
it's-
Oh, where?
In QR code.
that's what he says.
It really is.
Really?
Oh,
I took a picture and then we scanned the picture. And
Now everybody's going through.
about Ethereum, it's a good thing.
the label of the transaction in the QR code says.
Yeah, these Bitonic people are good with puzzles.
Presentation.
Oh, okay.
Some people are really good with something.
Oh, hij heeft wel gelijk dus.
That's for you to
Oh, oké.
try to find a figure out.
En nu ben ik ook wel een beetje benieuwd. Dus dit is hoe jij je geld verdient. Kijk.
You can check the balance of the address.
Pak maar even.
Yeah, it's not that much.
So are the people helping you with coding Amico Pay, or is it really a project?
Well, Jannes has not promised anything.
That's the important part.
Let's see, he's going to do that right now.
That's the status.
We
Oh,
brainstorm one day and
Yeah.
that's it.
oh ja. Oh, dat is wel. Ja, alright.
Okay.
Peter, you don't believe in the advantage of side chains.
I believe in advantages that something is going to work.
I mean, if they work, it'd be wonderful, but.
As trusted entities, they work.
Yeah. The federated version, I think, works fine. As far as I can tell, I was actually the first person to come up with the idea and did a bunch of work on which I call fidelity bonded banking. And in fact, they use banking in the name, should probably go and tell you something about how it was designed. But, you know, I think the idea of like trusting miners with this stuff is very dubious. You know, you just set up such poor
Zeker,
incentives.
probeer te kijken of ik hem zeg maar op.
If I were wondering, I mean, the last thing I'd want is be in a position where I go seize funds.
Yeah, and because Webcam tried to sell liquid to us. CNS thing.
I mean, Liquid, I think works fine.
Yeah,
It's a reasonable model, but, you know, it's pretty obvious where the trust is.
Ik had een keer op vakantie,
Ja,
dus
dat
had
is
ik nog een
een
verborgen prullenbak ergens.
Ja.
Die kon ik met de camera niet meer wisten.
Ik begrijp het niet, hè?
You have no
Ik
confirmation.
heb het gevoel dat de QR-code een beetje
Ja,
belangrijk
maar
is.
je
Liquid Light.
Fast
Dat ze met veel blokjes toe zouden moeten kunnen.
Steeds ik
And the
kunnen
problem
zien.
is with euros.
Ja, maar dus
Maar dat is
maar niet op zo'n manier dat je dus...
Het is juist om het beter te maken.
Liquid, it's
Ja,
only, at least if I've heard it, it's only a really denominated Bitcoins.
Want als er op één plek een reflectie zit of zo,
Ja,
heb die één pixel niet kunt zien.
daarom heb je ook die
Well, the thing is, like a
grote
liquid
blokken.
transaction,
Ik geef de hoe.
can be cleared, it's,
Ja. Maar goed, het is niet...
right?
Als je met een klein blokje daar is,
You know, if I want your exchange, I say
Yeah.
BTC.
Ja,
ja,
Oh, is het zo?
Ja.
Online.
anders kun je
Well, yeah,
qua
but no,
perspectief kom je er niet uit.
I mean,
Als je maar
liquid
niet
approach
kunt,
is more sanely implemented as,
I think it's
yeah, oh, it is. Yeah, I think it definitely.
Yeah.
There's all this trust involved, and it's just as
Ik
fast.
heb bij,
Maar de video iets heb ik in principe gepland.
ja,
So that's, yeah.
ik heb op computer vision bij de gestudeerd. Maar